Alright, so with a strong acid weak base titration, we initially start off with just weak base, and therefore, since that's all we would have present, we would need to use our Kb expression to calculate the amount of hydroxide that is made by that weak base. Use that to determine the pH via the pOH. Since the weak base is the major species present, our pH would have to be basic, greater than 7. As we start to add strong acid to our mixture, we create a buffer. Once we have neutralized all that strong acid up to the equivalence point. And so since we have both weak base and conjugate acid present, we can use Henderson-Hasselbalch, but we would expect the pH still to be greater than 7. Once we reach the equivalence point, we only have conjugate acid present. And since conjugate acid is all that's remaining, we would use equilibrium in our Ka expression to calculate the pH, but we would expect the pH to be acidic at that point. And then after we pass the equivalence point and we have destroyed our buffer, the dominant species is going to be strong acid. We actually will have two acids present, strong acid and weak acid. Strong acid is going to determine the pH, and we can go straight using our pH equation to do that. The pH will be even more acidic, so it will still be less than 7. Hopefully you're seeing some similarities between the weak acid strong base titrations and the strong acid weak base titrations. It's basically just mirror images, and we just switch from base to acid. Okay. So our first example here, we have ammonia. It's being titrated with the nitric acid, our strong acid. Initially, all we have is ammonia. We haven't added any nitric acid. So these first two equations really aren't going to play a role since we haven't added any of the acid yet. So we'll talk about those more on the next slide. The ammonia is going to be what determines our pH. Ammonia cannot donate a proton, at least not willingly. It is able to accept one. So in the presence of water, it's going to make ammonium ions and hydroxide ions. The Kb of ammonia is 1.8 times 10 to the negative fifth. And so with that concentration of ammonia, since that's all we have available, the ammonium and the hydroxide are going to be at 0. The ammonium is going to go down by x, and the ammonium and the hydroxide are going to increase by x. So at equilibrium, we know that the two products are relatively going to change by the amount of x, and the ammonia is going to stay fairly constant at 0.1. So once we calculate our change in concentration, our x, we get that the concentration of the hydroxide is 1.34 times 10 to the negative third. We can use that to calculate our pOH of 2.872, and then our pH would be 14 minus that value, 11.128. So again, we can tell from this one that it is going to be basic, that the ammonia is the major species, and that our pH is going to be greater than 7. Once we start adding acid to our mixture, we're going to make the conjugate acid of our ammonia. And so that was what you saw in that first equation there. The ammonia in the presence of nitric acid is strong acid, which will completely dissociate. We'll make ammonium ions and nitrate. Nitrate will be a spectator ion, so in the net ionic, the nitrate ions are going to go away, leaving us with the ammonia and the hydrogen ions making ammonium ions. Because we have strong acid, we need to determine stoichiometrically which reactant is limiting using our volumes and our concentration. 0.01 moles for the ammonia and 0.005 moles for the hydrogen ions. The hydrogen ions are going to be our limiting reactant, so we're going to go down by 0.005. We also initially have no ammonium present. So the reactants are going to decrease by 0.005 moles. The ammonium is going to increase by 0.005 moles, and that's going to leave me with equal amounts of the ammonia and the ammonium ions. This would be your halfway point when you have equal amounts of that weak base and the conjugate acid. And then we can use Henderson-Hasselbalch to determine what our pH will be. we do need to have the Ka for ammonia as opposed to, the Ka for ammonium as opposed to the Kb for ammonia, if we're using the pH form of Henderson-Hasselbalch. So ammonium has a Ka of 5.6 times 10 to the negative 10th. The pKa of that would be 9.25, and because the moles of the base and the acid are equal, that pH is going to be determined solely by that using the 9.25. Okay. In the next one, I think I'm going to be adding even more hydrogen ions. So we're still going to have a buffer present, but at this point we're going to have used up more of the base, and we're going to have more of the conjugate acid present than the base. So we're going to be seeing our pH getting more acidic. We will have 0.0025 moles of the ammonia and 0.0075 moles of the ammonium ion. So because this is still a buffer, we still have weak base and conjugate acid. We could still use Henderson-Hasselbalch. Both of these would be the major species, but the ammonium would be present in a little bit greater of a concentration. So our pH is equal to the pKa, 9.25, and because this is a ratio, we do not have to change these back to concentrations. We will expect to see that our pH is going to be dropping from that 9.25. It's still going to be basic, but it's going to be lower than the pKa value because we're getting closer and closer to that equivalence point. In this next example, I do believe we have reached the equivalence point. So this is one I would expect you to be able to calculate for me. We have the moles of the base, and we have the moles of the acid, and we don't have any of the ammonium to begin with. Both reactants are limiting, so we've used up all of our hydrogen, our strong acid, and we have consumed all of the ammonia. We no longer have a buffer, all we have are ammonium ions. We can determine the pH of the ammonium ions using the Ka of ammonium and showing how it produces hydrogen ions when placed in water. We do need to account for the new concentration. We have 200 mils now of the 0.01 moles of ammonium ions. So our concentration is going to go down to 0.05 molar. And this point we have used all the ammonia and we have used all the hydrogen. So we need to figure out how much of each of those are reformed from the ammonium that was made by using our equilibrium expression. We do need to use the Ka this time since we're making hydrogen ions. 5.6 times 10 to the negative 10th equals x squared over 0.05. Our x is our source of hydrogen, so we can go straight to pH with this. And we do see the pH has dropped quite a lot. We were at 75 mils in the just below 9. Now we're all the way down to 5. So when you are at the equivalence point and all you have left is acid, whether it be weak acid or strong acid, your pH is going to be acidic. The final example for this part is going to be when we have added an excess of the nitric acid. We have the moles of the ammonia and the moles of the hydrogen ions. And because we have used all of the ammonia, since that's our limiting reactant, we're going to have excess hydrogen ions. We also have ammonium ions present. The strong acid is going to be the major species. Strong always wins out over weak. And so with the moles of the hydrogen ions, we do need to find its new concentration by accounting for the volume of 250 milliliters. But we can use the moles to the volume amount to find our hydrogen concentration, and then our pH, 1.70. So because we only have strong acid present, we do see the pH has dropped quite substantially compared to when we had our buffer. So this particular example is just asking you to do the calculations at the halfway point and the equivalence point. You have a weak base, you can see that because you're given that Kb value and it's got an ammonia group, NH2, and you're adding strong acid to it. So at the halfway point, that's when your pH is equal to your pKa, because you have equal amounts of that weak base and its conjugate acid. So if we know the Kb of our methylamine, we can find the Ka by taking 1 times 10 to the negative 14th and dividing it by that Kb value. And if we take the negative log of our Ka value, we can get the pH of 10.6. It's still basic, but it's kind of in the middle of that basic range. At the equivalence point, we have used up all of the an original base that we had, along with our original acid. We had 50 mils of 1 molar methylamine, and we have 0.5 molar HCl. So to find the volume of the hydrochloric acid we would need to get that equal amount, we can use M1V1 equals M2V2. Okay. We know we have 0.05 moles of the methylamine, and we know we want 0.05 moles of the hydrogen ions. And so both of those get consumed, leaving us with 0.05 moles of the methyl ammonium ion. We can't find the concentration of that methyl ammonium ion until we find the volume of the hydrochloric acid that we needed to produce 0.05 moles of hydrogen ions. Okay? So to get that volume, and you can see that over there underneath the Ka expression, we would take the moles, the 0.05 moles of hydrogen we made, and divide it by its concentration, 0.5 molar. And that tells us that we needed 100 mils, okay, roughly double the volume we had of our base, since our concentration was roughly half, of that hydrochloric acid to have equal amounts of hydrogen ions and methylamine ions, okay, or methylamine present in our mixture. So the new volume would be 150 mils. So we would take the 0.05 moles of the methyl ammonium ion and divide it by the 0.150 liters, and that gives us a concentration of 0.5 molar. Okay, 0.05. I'm not 100% sold on that. Give me 1 second. Alright guys, so I went back and did the calculation. I'm guessing I cut and pasted this from a previous slide. But if you take the 0.05 moles of the methyl ammonium ions and divide it by the new volume, the 50 mils of the methylamine plus the 100 mils of the hydrochloric acid that's been added, you would get that the concentration is actually 0.33 molar. That is what's going to decrease. The products are going to increase. So using the Ka value, which we can get from the Kb, 2.5 times 10 to the negative 11th, we would set that equal to x squared over 0.33 molar. We can use that to solve for x squared, 8.3 times 10 to the negative 12, and then for x, 2.9 times 10 to the negative 6. X is a source of hydrogen ions, since this is a weak acid we started with, so we can use that directly to find the pH. And we would expect the pH to be acidic, since that's all we had present was a weak acid. This is obviously a fairly weak acid, since the pH is much, much closer to 7 than it is to 0. Okay? And then the last part we're going to talk about are indicators. Indicators are organic compounds that are acidic or basic. We pick an indicator to show the endpoint of our titration by finding one that changes color, hopefully close to that equivalence point. You do have a chart in your book you can use to reference this. I would most likely just give you a range of indicators and tell you the pHs at which they change colors. If I wanted you guys to figure out a question about what would be an appropriate indicator to use. This is a chart. I think this is from the previous textbook. I don't think this is the one out of your book. But hopefully you can kind of see the relative color changes that occur. You've used the methyl orange, and we see that that one changes in the acidic range from like an orange to a yellow. We've used the bromothymol blue, which is changing around 7 from yellow to blue. And then we've also used phenolphthalein, which changes from colorless to red and the basic range. So depending on what pH you expect to have your equivalence point fall around, you want to pick an indicator that hopefully is going to change colors in that area. So it says using the figure in 18.10, which one would be appropriate for a pH of 2. So if we go back to a chart here, we can kind of see that Crescel red is changing from orange to yellow just before 2. Thymol blue is changing orange to yellow right around 2. Erythrocin is changing just after 2. I wouldn't want to use the 2,4-DNP since it changes around 3. So my guess is that I chose just the Crescel red and Thymol blue. And you would go through the same type of logic for these other ones. So for a pH of 6.4, we would want to find on our chart around 6.5. We notice the Aerochrome changes right around 6. Brome Crescel purple changes like from a yellow to a reddish to a blue around 6.5. Alizarans changing around a yellow to an orange. And then Brome Thymol blue is again close to that 6.5 to 7 range. And so you can kind of tell that I put all 4 of them down. You're never going to find one that's going to fall exactly where you want it to fall, but you want one as close as you can to it. If we go back and look at 8.1, so we're looking right around 8, we see Thymol blue is changing from yellow to blue around there. The Crescel red up here had already changed basically from yellow to orange around 7.5. That at 8 we have Phenol red that changed kind of from a yellow to a red. We have the M-nitrophenol that changed from colorless to yellow. The orthocresylphthalate is changing from colorless to orange around 9, and the same thing around phenolphthalein. So you've got a few that are changing in that ballpark. I didn't put all of them down, I put some examples. And then if we did the same thing for 9.5, I believe if you go back and look at that 9.5, you don't have as many to choose from. Because this one changed back before 9, this one changed, it looks like it's starting to change before 9. Thymolphthalein is the one that's pretty much changing right on 9.5, and the alizarin's not really changing until you get closer to 11. So I felt like that one was probably most appropriate with thymolphthalein, but I could see you making an argument for a couple of the ones that we listed up in 8.1. Okay? Alright, so that's the end of this particular video, and this should get you through the titration section of your homework.